Hi, this lesson is about the indefinite integral and the net change theorem. So an indefinite integral is where we'll start. An indefinite integral looks like this. It looks like the definite integral, except it doesn't have limits. So when you take the antiderivative or evaluate the integral, it will be capital F of x, the antiderivative of little f of x, but then you have to always add this constant. And if you recall from when we talked about antiderivatives, we call that constant the constant of integration, and c could be any real number. And that's because when you take the derivative of capital F prime, the derivative of a constant is just zero. So no matter what c is, f prime of x will equal little f of x. Okay, so let's integrate some of these indefinite integrals. So we are going to integrate example 1 here. This is the integral of 1/10 v to the fourth minus 2v plus 1. All right, so this is already in a format that we can go straight to taking the antiderivative by applying the anti-power rule, as well as the rule for a constant. So that's what you see here. You add 1 to the exponent and multiply by the reciprocal. The reciprocal of 5 is 1/5, but 1/5 times 1/10 is 1 over 50. That's what you see here. For the second term, 2v, you add 1 to the exponent, so that's why it becomes v squared. The reciprocal of 2 is a half. 1/2 times 2, or negative 2, leaves me with minus v squared. So the 2's cancel. And then the antiderivative of 1, the antiderivative of a constant is just that constant with a variable. So 1v is just v. And then again, don't forget to take to add the constant at the end. So to check this, and I suggest you check until you're really comfortable with these problems. So if you take the derivative of the answer, 1/50th v to the fifth minus v squared plus v plus c, that should equal what we started with. So remember, here it's just power rule. So you're doing things in a little bit different order when you're checking. So it's 5 times 1 over 50, that's 1/10. Subtract 1 from the exponent. Here, again, power rule, 2v. The derivative of v is just 1, and the derivative of a constant is just 0. So your integral value, or your antiderivative, equals what you started with. Okay, so in the next example, we have to do a little bit of algebraic work before we take the antiderivative, because we have a product of 2 root x times this trinomial. So the first thing we need to do is distribute the 2 root x across those three terms. So in order to do that, I first rewrote 2 root x as 2x to the 1/2, which is what you see here. And so when you distribute, you have to add your exponents, because when you multiply exponential expressions, you add the exponents when they have the same base. And you also just multiply the coefficients. So 2 times 3 is where the 6 comes from in the next line. And 1/2 plus 2, adding your exponents, gives us 1/2 plus 4/2, which is 5/2. And you continue doing that across to all three terms. So the second one is 2x to the 3/2. The last one is 10x to the 1/2. And remember, we haven't integrated yet, so you still need your integral symbol and your differential of dx. All right, so in the next line is when we apply the anti-power rule to all three terms, and that's what you see here. So it's 6 times 2/7 x to the 7/2 minus 2 times 2/5 x to the 5/2 plus 10 times 2/3 x to the 3/2. So where did all these numbers come from? You add 1 to the exponent and then multiply by the reciprocal. So 5/2 plus 1 is 7/2. The reciprocal of that is 2/7. So the 2/7 gets multiplied by the coefficient of 6. Similarly, we add 1 to 3/2, that gives us 5/2, multiply by the reciprocal, which is 2/5, and also bring down the 2. That was the coefficient before. Same thing here, add 1 to 1/2 gives us 3/2, multiplied by the reciprocal, which is 2/3, and the 2/3 gets multiplied by 10. So when you simplify, you see the answer here in this pink box. It's 12/7 x to the 7/2 minus 4/5 x to the 5/2 plus 20/3 x to the 3/2 plus c. So unlike the previous example, if I were to check this, I wouldn't get back to where I started because of the algebra that we did. So if you were to take the derivative of what you see in the box, you would get back to the integrand that you see here after you expanded it. Okay, so let's move on to another example. Here in blue, I have the integral of 5 over the square root of 1 minus square root of 1 minus t squared dt. All right, so the first thing I'm going to do is factor out the 5. That's one of the rules of the properties of integrals allow us to factor out constants. So that's what you see here. And then at this point, you would have to recognize what was left, this one right here, based on the derivatives that you learned in previous chapters. So that's actually the derivative of your arc sine or your sine inverse function. So the antiderivative is just sine inverse of t multiplied by 5, and then add your constant. Okay, so memorizing the derivatives from previous chapters is a really important thing to have in mind. Otherwise, you won't recognize certain integrals. So here, the example in green, we want to find the indefinite integral of -2 secant theta tangent theta d theta. So just like the last example, I'm going to factor out the -2, the coefficient. So I'm left with secant theta tan theta that I have to find the antiderivative of. And this again should remind you of something. That's actually the derivative of secant. So the antiderivative answer is -2 secant theta plus c. Okay, so here in orange, we have to integrate the integral of 3 over x plus 5 dx. So similar to the previous two examples, I'm going to factor out the 3, which leaves me with 1 over x plus 5. All right, so I can't apply anti-power rule because I have two terms in the denominator, so I can't rewrite them in a different way. But hopefully you remember that the derivative of your natural log function is 1 over x. And this kind of looks like that. So the antiderivative is 3 natural log of the absolute value of x plus 5 plus c. So if you were to take the derivative of this, you would get back to where we started. Now, why is it in absolute value? Why do we have x plus 5 in the absolute value? And that's because of the domain of natural log. The domain of actually any log function is all positive real numbers. And since we don't know what our limits are, we want to make sure that this would only get evaluated for positive values. Otherwise, it wouldn't make sense. All right, so let's look here to the one on the right. We want to integrate t squared minus 1 over t to the 4th minus 1 dt. So again, nothing really stands out in terms of like, is that the derivative of any functions that we already know? I can't rewrite them as individual terms, but I can simplify it to see if it looks like something that I am familiar with. And we're going to simplify that by factoring the denominator. The denominator is the difference of perfect squares. So when you factor, you get what you see here, t squared minus 1 in the numerator, and t squared plus 1, t squared minus 1 in the denominator. Well, the t squared minus 1's cancel, so I'm left with 1 over t squared plus 1 dt, and that should look familiar. That's actually the derivative of arctangent or tan inverse. So the antiderivative is tan inverse of t plus c. So if these don't ring a bell, I highly recommend that you go back to look over all of your derivative rules from previous sessions. All right, here's another one. We want to evaluate the integral of 1 plus tangent squared of theta d theta. All right, so it's easy to take the antiderivative of 1, but tangent squared is not the derivative of anything that we are familiar with. So we're not going to be able to integrate this as it is, but it is one of the Pythagorean identities. So tangent squared plus 1 is secant squared. Therefore, I can replace 1 plus tangent squared with secant squared, which is what I did right here. And secant squared is the derivative of something we're familiar with. Secant squared is the derivative of tangent, so therefore the antiderivative is tangent of theta plus c. Okay, let's move on to this one here in purple. We want to integrate 5x squared plus 3 over x squared plus 1 dx. So again, this one doesn't look like anything we're familiar with, and I can't separate this into individual terms so that I can use anti-power rule. We don't have an anti-quotient rule, but there is another trick we can apply here, and this trick is often used when the degree of the expression in the numerator is equal to or greater than the degree in the denominator. So here, the degree in the numerator is equal to the degree in the denominator. Okay, and the trick is to apply long division so that we can rewrite this in a different way. Okay, so that's what I did here. I'm dividing 5x squared plus 3 divided by x squared plus 1. All right, so the way you do long division, for if you've forgotten, is you take the first term inside the dividend and divide it by the first term inside of the divisor, and that gives me a value of 5, which is what you see here. And then the 5 gets multiplied by the divisor, so you take the 5 and you multiply it by x squared plus 1, and that's the result that you see here. And then the top line and the bottom line, these two here, get subtracted. So when you subtract, you have to distribute that negative across. So the 5x squareds cancel, and 3 minus 5 gives us negative 2. Negative 2 is the remainder. So you can rewrite the original expression as 5 minus 2 over x squared plus 1, and they are equivalent. So this is equivalent to this. So that's exactly what I did here. I rewrote my integral in a different way. So I have the integral of 5 minus 2 over x squared plus 1 dx. This is something I can work with. So I'm going to split this up into two separate integrals and also factor out the 2 from the second one. So that's what I have here. So I'm integrating 5, and I'm integrating 2 times 1 over x squared plus 1 dx. Well, the antiderivative of 5 is 5x. Remember, you just attach a variable. And the antiderivative of 1 over x squared, well, that's, again, your arctan or your tan inverse. So you get minus 2 tan inverse of x, and then you add your constant. All right, so let's move on to the net. The net change theorem, so we're going to revisit the fundamental theorem of calculus part 2. So we'll be working with definite integrals again with net change. So the integral of the rate of change of f of x on a closed interval from a to b is the net change of the antiderivative on that interval. So that's exactly what you see here, and this actually is the fundamental theorem of calculus. So you can think of net change problems as the opposite of related rate problems. Remember, with related rates, we were taking derivatives, and this time we'll be integrating to find our result. So here are some interpretations where you would be using net change. So let's just talk about number 1 here. So if v prime of t is the rate at which water flows into a reservoir at time t, then the integral from t1 to t2, meaning 2 different times in my limits, of v prime of t, and I forgot to write my dt, is equal to v of t sub 2 minus v of t sub 1. And what that represents is the net change in the volume of the water. So the derivative is how fast the water is flowing into the reservoir. As water flows in, the volume is changing. When you integrate that, you actually get how much of a change there has been in volume. So let's look at the second example. If C prime of t is the rate of a chemical reaction at time t, where C of t is the concentration of the substance of a chemical's reaction time at t, then the integral from t1 to t2 of C prime of t is, and then again, that's with respect to time, dt, is equal to C of t sub 2 minus C of t sub 1. That represents the net change in the concentration of the substance. So we know that as there's some sort of chemical reaction to a substance, it is either getting more concentrated or less concentrated. There's some sort of change in concentration, and so the integral represents that net change in concentration over a time interval. Okay, so if dn dt is the rate of growth of a population at time t, then the integral from t1 to t2 of dn dt is n of t sub 2 minus n of t sub 1. And what that represents, it's the net change in population. So how much the population has grown or reduced over a particular time period is what the integral represents. Okay, next example is more business-oriented. So this one says if C prime of x is the change in cost of x units, that's considered to be marginal cost, where C of x is the cost of producing x units of a commodity, then the integral from x sub 1 to x sub 2, remember x sub 1 and x sub 2 are number of units, of C prime of x, and remember, always put your differential, sorry I forgot that in several places, that's equal to C of x sub 2 minus C of x sub 1, and that represents the net cost of producing units from x sub 1 to x sub 2. So it's the change in cost from one unit to another. All right, this next one should be more familiar to you. So it says if s prime of t is equal to your velocity, and remember we call s our displacement function. So the velocity of an object moving along a straight line that's considered to be rectilinear motion at time t, then the integral from t sub 1 to t sub 2 of v of t with respect to time dt is equal to s of t sub 2 minus s of t sub 1. That represents the net change in displacement or position of an object. One important difference is to note that distance traveled is not necessarily the same as displacement. So we compute distance by taking the integral from t sub 1 to t sub 2 of the absolute value of v sub t dt. And so when you're dealing with integrals of absolute value, you'll have to figure out where the function is equal to 0 and then determine if you need one integral or two different integrals, and we'll practice that later. Last one, if v prime of t is a of t, right? If the derivative of velocity is acceleration of an object at time t, then the integral from t1 to t2 of acceleration is v of t sub 2 minus v of t sub 1, which is the net change in velocity over that time interval. All right, so let's move on. Let's actually start practicing some of these types of problems. So first problem says if w prime of t is the rate of growth of a child in pounds per year, what does the integral from 5 to 10 of w prime of t dt represent? Well, if you were to integrate w prime of t, you would get w of t evaluated at 10 and at 5 and subtract them by the first fundamental theorem of calculus. And what that represents is the net change in weight of the child from ages 5 to 10. Okay, let's do another one like that where we're just interpreting what it means. Number 2, if oil leaks from an oil tank at a rate of R of t gallons per minute at time t in seconds, what does the integral from 0 to 120 R of t dt represent? So the integral from 0 to 120 of R of t dt, the antiderivative, I'll call it capital R, is capital R at 120 minutes minus capital R at 0 minutes, your lower limit. And so what that represents is the number of gallons that leaked from the tank from 0 to 120 seconds, which basically means in the first 2 minutes. It should be seconds. All right, so now let's actually integrate these problems. So number 3, particle moves along a line so that its velocity at time t is v of t equal to t squared minus t minus 6 in meters per second. Find the displacement during from seconds 1 to 4 for t between 1 and 4. And then part B will be to find the distance traveled over that same time interval. Okay, so for the first part for displacement, it's very straightforward. You're just integrating the velocity function. So that's what you see here. So it's just 3 separate terms. We're applying anti-power rule and the rule for a constant to take the antiderivative, which is what we get in line 2. And then we have to evaluate it at 4 and at 1. So that's what you see in this line. First we plug in 4 and then we subtract out, and that's why the subtraction symbol is here, and we need parentheses in order to group that minus sign with those 3 terms. So when you compute that, do the arithmetic, you get the following line right here. So in the next line, I combined the fractions, the 64 thirds and the 1/3 to get 63 thirds. I wrote the 1/2, and then I combined all of the integers, and they worked out to be minus 26. So 63 divided by 3 is 21, which is what you see in this line. 21 minus 26 gave us -5, and -5 plus 1/2 is -4.5, which means that the object, the displacement of the object is 4.5 meters to the left. That's what the negative represents. Okay, now we're working with the same problem to find distance. To compute distance, we have to take the absolute value of the velocity function from 1 to 4 and integrate that with respect to time. So in order to determine how to integrate, we don't really know how to integrate an absolute value. We need to get rid of that absolute value in some way. So we have to figure out where v is equal to 0. So we take our integrand, set it equal to 0. We get 2 solutions, 3 and -2. Well, -2 is not within our interval of values from 1 to 4. So we're working with t equal to 3. All right, so now I have to figure out where is my velocity function positive or negative with respect to left and right of 3. So here on this number line, I put 1 and 4, which are my lower and upper limits, as well as my solution to the previous equation, which is 3. If you plug in a number between 1 and 3 into your velocity function, you get a negative result, right? You plug in, right here's the easiest way to find it, get a negative result. And if you plug in something between 3 and 4, like 3.5, you get a positive result. Okay, so that means that I'm going to split up my integral into 2 separate integrals, one from 1 to 3, and the other one from 3 to 4, because the behavior of the function is different to the left and right of 3. So to the left of 3, between 1 and 3, the absolute value function would change it to positive, which is the same thing that putting a minus in front of the function will allow us to do. So we've now rewritten our absolute value function in a different way as the negative of the t squared minus t minus 6. And that negative belongs to all three terms. And then from 3 to 4, it's positive, so you can go ahead and drop the absolute value and integrate it from 3 to 4, t squared minus t minus 6 dt. All right, so we've done this trick with absolute values before with limits. So in this next line, I distributed the negative to the first integral. So I'm integrating negative t squared plus t plus 6. The second integral stays the same. Now we're ready to take the antiderivative. When we take the antiderivative, you no longer write your integral symbol and your limits go to the right. So I have negative 1/3 t cubed plus 1/2 t squared plus 6t, and we have to evaluate that from 1 to 3. And then 1/3 t cubed minus 1/2 t squared minus 6t, and we have to evaluate that from 3 to 4. Now in this next line, we plug in our limits. Remember, always plug in the upper limit first minus the lower limit. So I did that in this line here. So you see all the work, indicate it right here. And then we simplify, you do the arithmetic. So we get this line here. So there's a lot of numbers on this line, so I looked for things that would cancel out immediately. So this -9 and this -9, that's -18, canceled with this 18, so I didn't have to worry about that. Then I combined all of the fractions with 2 in the denominator, so I got 17 halves, and then I combined the fractions with 3 in the denominator, these two, and I got 65 over 3, and I combined all of the integers that were left to get -20. So that means that I have a common denominator of 6, which is what I got here. And when you reduce that, that's 61 over 6, which is 10 and 1/6 meters. So the distance traveled by the object is 10 and 1/6 meters. And if you recall, that is quite different than the displacement of the object, which was 4.5 meters to the left. So distance traveled and displacement are not necessarily the same, although they can be. All right, so number 4. Water flows from a storage tank at a rate of R of t equal to 200 minus 4t liters per minute, where 0 is less than or equal to t less than or equal to 50, and we want to find the amount of water that flows from the tank in the first 10 minutes. So we're only interested in what happens from minutes 0 to 10, so that's what you put in your integral. We're evaluating it from 0 to 10, and the rate is 200 minus 4t dt. So you take the antiderivative, you get 200t minus 2t squared, evaluated from 0 to 10, plug in your limits, and don't forget here, I already distributed the negative, which is why that second term turned positive. So you end up with 2,000 minus 200, so that means that 1,800 gallons of water flowed from the tank in the first 10 minutes. Okay, let's move on. So we want to find the displacement over the time interval from 1 to 7 of a helicopter whose velocity, vertical velocity, because it's going upward, is v of t equal to 0.06 t squared plus t in meters per second. All right, so remember, displacement is just the integral of velocity. So we are integrating from 1 to 7 of your velocity function. So you take the antiderivative seen here in line 2, add 1 to the exponent, that's where t cubed comes from, multiply 0.06 by a third, so we get 0.02 t cubed plus 1/2 t squared. Now we're ready to plug in our limits. So you substitute the upper limit first and then subtract when you substitute the lower limit. So I've already subtracted and distributed, which is why that term turned negative. So then you simplify and you get what you see in this line, 343 over 50 plus 49 over 2 minus 1 over 50 minus a half. So I combined the fractions with a denominator of 50 first, so that's 342 over 50, and then the ones with 2 in the denominator, so that's 48 over 2. They both simplify. So 342 over 50 are divisible by 2, so this gives us 171 over 25, and 48 divided by 2 is 24. So that means I have a common denominator of 25, which is what you see in this line. Now you're ready to add your numerators, so you get 771 over 25, which reduces to, as a rewritten as a mixed number, is 30 over 30 and 21/25 meters. As a decimal, that's 30.84 meters, and that's your displacement. Okay, here's another one. A projectile is released with an initial vertical velocity of 90 meters per second. We want to use the formula v of t equal to 90 minus 9.8 t for velocity to determine the distance traveled in the first 16 seconds. Remember, when you're asked for distance, you have to take the absolute value of the velocity function. So that's what you see here. This is the integral we have to evaluate, the integral from 0 to 16 of 90 minus 9.8 t dt. So similar to the previous example where a couple examples ago, where we found distance, you have to first figure out where your velocity is equal to 0. So that's what I did here. Set it equal to 0 and solve it. And you get that when your time is 9.18 seconds, your velocity is 0. So that means it's reached its highest point and then it's starting to come back down. So now we have to check what is the sign of velocity to the left and right of 9.18. So on this number line, you see my limits, 0 and 16, as well as the time value that I solved for. You plug in a number somewhere between 0 and 9.18 into your velocity function, which is here. And if you do that, you get a positive result. And if you plug in something greater than 9.18, but less than 16, like let's say 10, you get a negative result. So when you set up your integral, it's actually going to be set up in the opposite order than the other example we did, where your first integral from 0 to 9.18 is just the velocity function itself. But for the second one, you need to put a minus sign in front of it because of the sign we found here. So it's minus 9.18 to 16 of 90 minus 9.8 t. So in the next line, we actually take the antiderivative. So that's what you see here. I have 90t minus 4.9t squared evaluated to from 0 to 9.18. And then in this one, I distributed the negative and took the antiderivative. So that's negative 90t plus 4.9t squared. But this time we're evaluating from 9.18 to 16. So when we substitute in, according to the fundamental theorem of calculus, we plug in our upper limit minus our lower limit. That's what you see here. When you compute all of that, you end up with 640.93 meters as the distance traveled by that object. Okay, we have one more. We want to find the net change in velocity over the interval from 4 to 5 of an object with an acceleration of 23t minus 2t squared in meters squared per second. That's incorrect. In meters per second squared. Okay, so the net change in velocity is the integral of acceleration. So remember, the derivative of velocity is acceleration. Now we're going in the opposite order. So we are integrating from 4 to 5, 23t minus 2t squared dt. Take the antiderivative, which is what you see here, do anti-power rule. Then we substitute in our limits, put in the upper limit first and subtract out your lower limit. Don't forget to distribute that minus sign, which is why this term is negative and this one here is positive. And then we expand this, right? We square and cube the appropriate numbers. We end up with these 4 fractions here. So I combined the ones with similar denominators in the next line. And then I got a common denominator of 6. So your result is 377 over 6, which is 62.83 meters per second. Remember, we were solving for velocity, so you have to include the appropriate units. Okay, so that's it for this section. You're ready to try the homework. Good luck.